Welcome back. Okay, so now we're going to look at how you pre-process your time series data before you do any forecasting. So that can be important for a number of reasons. The first reason might be just to remove some noise from the data so that the forecasting task is a simpler one. And we've seen that with calendar adjustments, and we'll go over that again. And the second reason is to do with the fact that over time, variance in the data might increase. And the alcohol data set is a really good example of where that's happening. Now, that when that happens, that can play havoc with your forecasting methods. So we're going to look at simple ways you can deal with that so that your forecasts will be more accurate. So what we're going to do is we are going to import pandas, numpy and matplotlib, so very straightforward. First of all, we'll recap calendar adjustments. So if you remember, we make a calendar adjustment when we're working with monthly level data, because every day in the month, every month of the year has a different number of days. So that leads to just the totals having a little bit more noise just to the variable number of days in the month. So there's a really simple adjustment you can make. So let's read in our alcohol data. Let's plot that. So if you remember, this is total sales of beer, wine and spirits, and we can see that that's increasing over time between 1994 and the end of 2019. It's also increasing in variance. So there's a simple way to deal with the calendar issue to start off with, and that's because built into date time indexes is this property called days in month. So on the sales data frame, on its index, its date time index, we'll just have a quick look at what's in those days in the month. So that returns this array, and inside the array you can see for each month there's a different number of days. So a simple way to adjust is just to divide through by that number. So you've got a total for January and you would divide through by the number of days in January in order to get a rate, the average number of sales each day in January. So we could do that on a single line. So we've got the sales data frame and the sales column, and we're dividing through by the days in the month, and that we're saving that in a new series called sales rate. And what you can see is this was in the thousands, and now and in whole units, and now we've dropped down to the average number in the hundreds, which is a floating point number. So one thing we didn't cover before was once you've produced your forecast, you'll probably want to give your client results in the same units that they gave you the data in. So you'll need to back transform your calendar adjustment, and that just means reversing the operation that you made in order to adjust it. So in this case, we divided through by the total number of days in the month. So to reverse that, to back transform it, all we need to do is multiply by the total number of days in a month. And that gives us numbers back in the thousands, starting off in the sort of low 3,000 to 4,000 and all the way up to nearly 16,500 by the end of the data set. So that makes sense. So that's the simplest type of adjustment you can make. You only ever make that when you're working with monthly level data. So a type of adjustment you might make to weekly, quarterly, or monthly, or even hourly data, or even data in seconds if you're going down to that sort of level, is an adjustment to deal with this problem of increasing variance. So if you look at our time series here, you can see that over time, the fluctuations appear to be increasing. So let's just plot that with a 12-month rolling average. And what we can see you can think of this average as the level of the data over time. And as that level increases, we can see that above and below it, those fluctuations are getting further away from the line. So that's what we call increasing variance. So that's a problem for statistical forecasting methods to deal with, unless they've got something built into them to deal with that kind of seasonality and change in variance. So that might not affect your point forecast. But what we're going to talk about in a later lecture is something called prediction intervals, and prediction intervals deal with uncertainty in your forecast. And what I can say is that if you don't deal with this problem, or your forecasting method hasn't got a built-in way of dealing with it, this will cause significant problems for your prediction intervals. So we need a simple way that isn't too complicated to understand to deal with this. So the simplest way is to take what's called the natural logarithm of that data. So you can do that via NumPy. There's a built-in function, np.log. So if we run that, that's taken the natural logarithm of the data. And now if we plot the same chart again, but this time with the log sales as opposed to the raw sales, our time series now looks like this. So what you should be able to see is that the fluctuations above and below that orange line, the level of the data, hasn't increased over time. It isn't changing with the level of the data. So that means we've stabilized our variance over time. And the consequence of that is that time series is easier to forecast, and your accuracy of your forecast in terms of your point forecast maybe, but definitely your prediction intervals will be much more accurate. Mathematically, to back transform this data is a little bit more complicated. So you need to, the reverse of a natural logarithm is to exponentiate it, and to do that there's a built-in function within NumPy called exp, and all we say is np.exp and pass in our log sales, and that returns things back to the units that we're working in, the average sales. So once you produced your forecast, you would pass it into this function, and that would give you your point forecast back in the units that you would want to talk to your decision maker about. So you don't have to take a logarithm. There are alternative ways to transform your data. Two simple ways are what you call power transformations. And they're called a power transformation because you're taking either a cube root or a square root. So your data is being put to some power, either a third or a half, which is the cube or the square root. So we'll take the cube root here. CRBRT stands for cube root sales, and there's a NumPy function for cube root, which is CBRT. Let's run that. Very quickly, that's produced the cube root of all our sales rate data. And if we plot that, what we can see is that has also done a reasonably good job of stabilizing variance over time. We can also take the square root, which is the numpy.sqrt function for square root. Plot that. That is perhaps less good in this circumstance. It's pretty close. But perhaps it's not squishing these upper values as much as the cube root or logs. And then what you can do is you can do a comparison if you like. So here I'm going to plot both the log sales and the cube root sales and make a decision about what transformation I should be using with this data. So from that, I would say that the natural logarithm transformation is the better of the two. So I think that does a better job of giving me a linear trend and squashing the variance at the higher end of the time series. So for forecasting this time series, I would definitely use a natural logarithm approach. And in general, that's what I've tended to use. However, it is always worth checking out power transformations to see if they are appropriate or not. So that's a very quick talk through of transformations. So it's just a check you need to do before you move on to forecasting about, does my data actually make sense in terms of the forecasting method I want to use. So now in the next lecture, we will look at prediction intervals, and we will use some transformations within that to make sure that we're getting accurate prediction intervals.